Okay, thank you. Do you see the slides?
Yeah, everything looks good.
It's okay. Okay. Welcome everybody. I'm Lotfi Gadri. I'm department manager for the embedded and communication systems at CETIC. And I suggested this webinar around the issue of managing IoT data in industrial application and processes, since this is a general issue with the IoTs today, is that we have a big heterogeneity. So we will develop what we mean by heterogeneity, how we can deal with it. So just to be clear, I don't have the solution, the miracle solution to manage this heterogeneity, but I have good advices through this webinar how to deal with it. Okay, and I will start the first part of the presentation by giving some high-level considerations and topics, and then we'll illustrate this through some results of research projects at CETIC. And some technical realization that deal with this issue. So what we mean by heterogeneity. So today, when you use IoT, no matter what the use case is, you need to have objects. These objects communicate through protocols, hardware interfaces. You have, on the other hand, also software applications, backend applications, databases, monitoring application that use the data produced by these IoTs. So here the heterogeneity comes from the setups that put IoTs into practice. So we have heterogeneity at different levels, and from heterogeneity of the hardware, heterogeneity of the protocols that carry the data produced by these different hardwares, sensors, actuators, equipment, and then we have the heterogeneity in terms of encapsulation, formatting of this data, specific to each protocol standard or also proprietary formatting. Then we have heterogeneity in terms of interfaces to software systems. We can push this data to application, to databases, to enterprise software that will exploit this data. And this goes both ways. You can have data that comes from this application and targeting the end devices. So this is a fact. So today, IoT is like that, and heterogeneity is a fact. So either we can deal with this issue by keeping only a small subset of IoTs and protocols and manage to be tied to this solution, but we will not take benefit from all the innovation that come with new technologies and data and so on. The other way is to say, well, in general, we don't have this heterogeneity from the beginning. We start with something. We start with the legacy system. We start with the current setup, and then we have technology that evolves, and then we need to integrate it. So the managing the heterogeneity essentially will consist of having a solution that manage the evolvability of the systems. So, do you see the next slide? Just to be sure. Are you seeing the slide need for evolvability? Okay.
Yes. All good.
Yes. Okay. So, as I said, we need to support evolvability to deal with the heterogeneity. So we need to have systems that are evolution capable. But what that means? We need first, evolvability means that you have to manage a kind of life cycle of your solution. You have life cycle consists of maybe at the first time assessing some technology components, then implementing them in small box proof of concepts, then integrating them to your solution, adopting them, validating, and then pushing them to the operation in the field. So this is, if you have a system that can manage all these steps without going from scratch, at each step, it's good. Then, but evolvability, the need for evolvability it comes from the need of offering some adaptability mechanisms. So we need to have our systems in the field that are easily extensible, easily interfaceable. I'm not sure that the word exists, interfaceability. So we need to have ways that are easy to interface them with newer system, with external systems, because they need to exchange data with third parties, with other equipment in the field, and more and more we need to share data between different application domains that are not that in the past were working in silos. So for example, today we need to maybe share data about the energy management, about the runtime execution during the manufacturing process, sharing with supplier, subcontractor, etc. So third point is the ability to develop that the system evolves, but in a controlled way. We see in the field a lot of systems that start very well and they are good for some months and some years, and then they become more and more complex, and complexity generates bugs, generates errors, productivity issues, etc. So especially in the software domain. So we need to have a system that is evolvable, but evolvable in a controlled way in terms of software and integration of the data from the field or from the application. So that's why we link the management of the heterogeneity to the management of the evolvability of our software systems that manage these IoTs. So master word is keeping complexity under control. Well, let's go deeper into this. So evolvability of IoT-based solutions, we will develop here why it is important, what are the criteria to take into account, and what is the potential that we can get from managing efficiently this evolvability. So in terms of importance, is as I said, we need to manage the end of life, for example, of existing and legacy system. When you have machines in your industrial environment, for example, that come to end of life, you will need to replace them. Components, sensors, actuator, need to replace them. But you want to do this smoothly, so without impacting or having long stop time of your processes, because you need to integrate this in terms of getting the new device into your system. So that's one issue. Technology replacement, migration, retrofit, or upgrading of new systems. We need to do it more efficiently. We need to do it more smoothly and transparently. Also, if you manage evolvability, that means that we avoid or at least limit the proprietary lock-in. What's this consists of having to be tied to one supplier for technology, one supplier for a solution, and having big difficulty to replace this component, to this module, this system, this software solution. So if you manage from the beginning to have systems that are evolvable, this will help you to switch from one supplier to another with a limited impact. It will never be without impact, but we need to keep this under control and also manage the transition between a technology and another, or a vendor of solution and another. Example, machines or sensors or the like. What is interesting for the business is, in general, the data that is provided by these objects, these devices. When you monitor a system, what you are interested in is not the temperature or the parameters supplied by a specific device, but you manage the physical data, and you need to be able to switch the supplier to give the same data value. Then the importance also of managing evolvability is that technology evolves, and we have each day, each year, new technology that become mature and interesting to integrate into our installation. Even if you are not in the innovation domain, you can get big benefits in terms of productivities, efficiencies, and savings in terms of euros if you integrate up-to-date technologies, interfaces, protocols into your process. So that's for the importance. So let's say, what are the criteria to implement this evolvability? Basically, there are four criteria. So if you need to have a solution, a system, software solution for your IoT. When I say IoT, I'm talking about the wider IoT domain. So it's not restricted to one IoT or one IoT domain. We speak more and more about industrial IoT, but this is just say buzzword to say we are in the industrial domain, but we are connecting with objects that provide data, and we use them in domain-specific processes. So the issue is basically this similar for other domains like smart energy or smart building or smart cities, but the use cases are different. To get to get the most from the evolvability is you need to manage these four aspects. So you need to think about your system architecture, or even for this, if you have smaller systems or embedded systems, you need to think them to conceive them in a modular way. That means you need to split the functionality in terms of modules. So, but modules could be specific functionalities, well-defined and specialized. But this is not sufficient. We need also to have these modules composable. So we need to think about the way we will make these modules interact with each other. Then, having modularity and composability, you need also to find a way to configure an instance of your system in let's say a user-friendly or practical way. So you need to have these modules interconnectable through a configurable way, and not very. So you need to have flexibility in terms of configuring these modules. They are parameters, internal parameter, but external parameters in terms of interaction with the other modules of your architecture. And finally, which is it's criteria, but it's criterion, but it's also a consequence of the previous attributes, is that you need to have all this stuff interoperable. Interoperable means that, well, you can have module A interoperable with module B, but in terms of evolution, maybe in some time we will need to have it interoperable with another module, and finally we will have maybe all the stuff fully interoperable. We need to think about that at the beginning. We cannot anticipate every evolution of the system, but we can think about it and have the architecture that supports it. So here, rather than, for example, in a simple way, rather than having connectors, odd-end connectors every time we need some interoperability with another system, it is maybe more interesting to think about way if we anticipate that we need to interoperate with other types of systems, to anticipate a way that is more easily implementable to exchange data. So there are several protocols or approaches that can support this evolution. Well, finally, what is the potential? So, okay, we see that maybe the evolvability is important, and we need to support some criteria. But what is the potential of all this approach? We can summarize it in these 3 points. So we can foster cross-sector synergy. Today, systems cannot continue to work in silos. If we are in the mobility domain, we will need to deal with some aspects that are relative to the energy. We talk more and more about environment, circularity. We have some common things in the IoT over several domains. So if you manage the evolvability of your IoT solution, you can easily interconnect and get benefit from synergies with other domains. Also, you can leverage the experiences and the best practices from these other domains and avoid reinventing the wheel, like we can say. Also, it's mean to facilitate and accelerate the adoption of technology, so allowing them to be tested, evaluated in real condition easily, more smoothly, and more effectively. And finally, you can manage the evolution of your system in continuous way. So you can, if you have support for evolvability, you can, for example, in a factory, if you need to add new sensors, you can do it on and exploit their data. You can do it without disturbing the system in place, and do it progressively by testing these technologies alongside with your system in place. And this is very important, because in industrial domains we know that it is in general very difficult to stop the process, to add something and test it in the field. Well, I'll say let's go to some more practical aspects. So how to deal with this all these challenges. So here at CETIC, we thought about this, and from an IoT perspective, the idea is that well, exploiting Internet of Things means creating connection between data producer, data consumer. So you can do it. You can do it the manual way, the ad hoc way. That means you create a connector between when you need a connector, you create it, and so on and so on. You can leverage some technologies, but you do it on the fly. And most of the solution today proceed like this because they don't anticipate the system getting more and more complex. Well, after some time, you will find this, the pipes you create will create something like this. And something like this is very difficult to maintain, to diagnose, and and it's time consuming when problems arise. So one of the hints or the idea to deal with this is to say, well, we need some kind of middleware, some kind of software in the middle that will take data and abstract from the data source specificities. Data source specificities are the technology, the hardware, the interface, the protocol, the coding of the data, and try to abstract from this and get the real data, so the data that we need for the application, and package it in terms of what what in the other side the application or the process needs as to be able to run. And what we can do also is to make this abstraction more relevant is that we add what we call semantics. That means what this data, okay, data is only digital stuff, 0 and 1s, and but semantics is the meaning that we give to this data. The temperature is something coded in 1 byte or 2 bytes, but we need something alongside with this that says, well, this byte is data with this signification, with this meaning, and we need to handle this meaning inside the middleware, and then application will discuss with the middleware in terms of meaning of the data and meaning of the data, and no more with this data comes from this protocol and this system and this equipment and this version of the firmware of the equipment and so on. We get rid of all of this. We abstract it in the middleware. How we prototype it? So we based our thoughts on the criteria that we mentioned before. So we want it to be something light with specialized modules. Modules do things that are well defined, and there are categories of modules. So in the data process, from the IoT to the application, we need these types of modules. We need some I/O support. This is specific to the interface in which we can get the data. Then we need to have some specialized modules in coding, decoding, encapsulating the data. Then, and this is the kernel of the system, we map the data into data we call data models. So it's some modeling of the data. So there were some initiatives, and there are several, let's say, some kind of standards or de facto standards that try to put to suggest some data models and the way we can handle it for different domains. For example, in the industrial domain, UPC OPC UI proposes a data model, but well, it's specific to the domain. But okay, the idea is that you get your data, you map it into a data model, and then you can distribute it in, out through connectors to the different consumers or exploiters of this data, which could be any software, enterprise software, or database. What is interesting here is the idea that you implement something in a modular way. You can push the modularity to the extreme, to the extremity, but well, you need to select what level of modularity you need. But if you don't think about it, well, your start is not good. Also, when you have this, it's easier to do what we call today edge computing or processing at the edge. That means you can rather than sending data, raw data, you can do some jobs before sending your data. If not all the data is relevant, you can do you can plug some computation on this data to filter the data, for example, or to aggregate the data. And in an extreme way, you can put even some custom processing in this data that goes from statistics to machine learning. Well, and when you do this, you can go easily from a model to a model, since you map your data in, you map your input data in a data model, and then if you need this data in another model, you can use translator, and you don't you are not obliged to create all the data flow from the sensor to your new application that exploits another data model. So here we see, well, the impact of putting some abstraction between the application and the specificities of the IoTs that provide the data. Well, and then, well, if you have these specialized modules, it's a matter of composing these modules to compose and configuring these modules to implement certain data flow that you need. Here is an example, but let's say don't pay attention to the technical words. Let's say this is a data collection flow that goes from a data source that talks in a protocol called KNLPP, but it could be a Modbus, it could be any other protocol, serial protocol or industrial protocol, and then you map this data. This data is used by an end application that is things about, say, monitoring application or for the data, or business intelligence backend or something like this. And in between, you take this data, you put semantics on it, and then the application can understand it without talking directly to the sensor. So here is an example of implementation. The colors are the specialized modules that we see that we get it from serial, then we map it to the an information or data model that implements the KNLPP, and then we get the relevant data, publish it to the information model on the other side that is understandable by the final application. And when you have these modules, if in case you change your data source, you will change only part from this data flow, not all the stuff. Okay, so and then we can build a global, bigger architecture that uses different data flows, compose them, map them into an internal data model that could be customized to the user and evolve with the needs of the user. And then, well, the idea is that you have your sources, you map them to the internal data model. It's It's kind of internal standard, and then you map it out to the different consumers on the other side, which are applications, for example. And all of this stuff needs to be done by configuration. Otherwise, you simplify from one side and you add complexity of configuration, and you don't get much benefit. So for this this middleware, we implemented some interfaces that are today supported, and from the well-known interfaces or connector that we find in data collection systems today. We work on support of new protocols, but well, what we need to understand is that the idea is not an accumulation of a library that accumulates the drivers for different protocols and so on. The idea that we provide a general way to implement it, and then this is the protocol that are here. It's a matter of implementing once and using many times. So, well, I will go along with that. To summarize, so here we have a middleware that that could take heterogeneous objects that provide data points. We map these data points, we multiplex them, we work them, we augment them, process them, and then distribute them in raw mode or in processed mode to different application. All the stuff is done by configuration of the middleware. Indeed, if we need to support, if we want to support a new interface or a new protocol, we need to add the support in the toolbox. And once the support is here, we can use as many data sources for this protocol as we want, because well, it's support. Some examples of deployment. So we worked with some companies in the industrial domain, but okay, it's simplified in this figure. We have a company that produces some industrial machines and wants to deliver them to customers, and wants to get an easy way to monitor them and to do maintenance for their customer. So this is the initial need. So then, after some time, they wanted to have they have different kinds of machines with different generations of hardware providing the information that is collected on the machine and around the machine, and they wanted to also to have different ways to transmit data to the central office. And all these machines are distributed geographically in different on the customer sites. So using the approach implemented in the middleware, it was really easy to prototype. We talked at the beginning about the life cycle of adopting new technologies. They do it firstly alongside the way they are collecting data from the machine. And then we implemented a kind of hierarchical data collection. So we have two levels, one at the end side and one that is collecting the data and presenting it to the software of the company. And the transition between the two was a matter of instantiating a new the central middleware and adapting the connectors. It was really very easy, and was really very easy and very quickly implemented because, well, we leverage the capacity of the middleware to support this evolvability through the modularity and the composability of the components in play. We have also developed some demonstrators at CETIC that in general, this demo it was a demonstrator for Industry 4.0 miniature that miniaturized that its goal was to show that we can have some flexibility in integrating very different devices from different providers in one demonstrator, and then we can evolve this demonstrator by adding new components easily, not going each time from scratch into integrating the new features. So it's an instrumented setup with some different robot and items, laser, and so on. And we collected the different data through an industrial gateway on which we put the middleware, and then the data was distributed to two different destinations, one for the real-time monitoring and one for the analysis in the long term. And this implementation was a matter of instantiating the connectors, and things could be done simultaneously for the distribution of data. For example, if you have several applications that use the data, it's a matter of configuration. And the idea was to show the capacity of modular, composable, configurable architecture to support multi-source, multi-protocol, and multi-destination in the implementation. We are going also, if you visit the CETIC in the next weeks, next months, we can show you some demonstrator in our demonstrator lobby that use this software component in different use case scenarios. We showed here two use case scenarios in the industry, and the most the one from the industry and the one from the demonstrator, the miniaturized demonstrator, but we use them in other use cases. For example, in smart building to interface energy data and monitoring data in building and air quality data in some projects, and we use it also to support the evolvability of our own building, because we are adding sensor, we are adding systems in our building, and we try to integrate all the data. And it's not only the data from the building, it's data from the users that are coming to the building, and from external systems, weather, and so on. Well, that's the end of my presentation. I hope I was not so long, and I will be glad to answer your question.
Yes, I have a question, if I can. Do you have, by chance, some example or use cases for the railway, with railway application, in order to understand more precisely in our sector how this can be used, please? Thank you.
Yeah, we work on other projects here. We are talking about usage of this kind of it could be embedded software to collect data from an embedded network, for example, inside the trains, because trains are also composable, and we need to adapt quickly in different configuration, and the idea is that we do it transparently. But we are still in this stage of thinking about the architecture and the high level needs before saying, well, it could be done, and how, and how we can implement it. But the idea is that we have different data, different places where we can collect data, and the configuration, no matter whether the configuration evolves, we need the system to be resilient or adaptive enough to get the relevant data. But well, you need to, let's say, brainstorm on further on the use case. It could also be done for the monitoring. For example, if we have in the railway, we can have different pieces of hardware that will for which we need to collect data to anticipate maintenance and so on. And this should be, if the process is static, no need for this solution. If you are doing the same stuff every time, no need. But if the configuration in the field may change, and it will change, for example, if you replace some components, you change a provider, you need to think about it, because, well, it's an investment in the beginning, but then you can get things on the rails.
Okay, I have another question, because when you say data, I imagine that you are saying big data, big quantity of data. And I wonder, once you have collected those data and you have them in a homogeneous, they are now homogeneous thanks to your middleware. I wonder, how do you manage those data? What other advanced technologies are you using? Maybe artificial intelligence, or some machine learning, or other things that can help in managing the data, and which is, let's say, one of the applications that you have already done in order to understand the full chain.
Yeah,
thank you.
Course. Yeah. Well, I spoke here from the rather from the embedded side of things, but of course we think about the full chain value of data, from the sensor to the backend. Let's say backend means application in the server or the database or something like all the stuff that is on the server. What we do at CETIC is that we have this is another department that works on data analysis. Their research is on systems that can handle data velocity, for example, or big volumes of data coming from different sources, and they work on so we have another solution that is, well, it's well adapted for the data from the field, because it is dedicated to time series, what you call time series. And when you use a backend system that uses time series, an efficient database, time series database, you can do your application will be performant. So because you will need to test quickly all this stuff of data, maybe having all time running processes that analyze the data. So here is a matter of the full architecture. So we need to know what are the volumes of data in play, and what IT infrastructure could be used and we may add also some requirement for some domains. I think also in the railways or in the aeronautic domain, we need to keep track of data even for years for the traceability of the component or things happening in the field. One requirement we see in critical domains is that you need to guarantee that you will not lose the data. And this is then you have here some highly some system that at runtime ensure that your data is not lost, even if your server goes down. This is natively replicated architecture from the server side. But well, this is another domain that needs to be taken into account in when you think about the full process of collecting and analyzing the data. What is the trends now also goes to we hear a lot of stuff about what we call edge computing, and this is mean to explore at best the resources, the computer resources that are near the devices. So because you have the end devices or the data sources, then you collect the data. But in general, the hardware you have to collect the data is capable of far more than collecting the data. And then, well, no, it's pushed by the trend of distributed learning. For example, we say the learning, machine learning. So rather than collecting all this stuff of data on server, which is costly in terms of communication and in terms of bandwidth and also in terms of cost in processing on the server, you can thought about collaborative architecture between the edge devices, the end devices, and the cloud. But this also poses some challenges in dealing with this in a transparent way and in a smooth way, because your computation, you need to give means for your system to do computation in a dynamic way, to deploy computation, because you cannot afford in programming your edge devices as you program your server. So
Ludwig, we have a question in the chat.
Yes.
It's about, the question is not only in the train, but if they can bring together information from the platform. So if somehow, I don't know if the question is whether to connect the train and the platform or independently the two. I guess both is possible, right? It's not a...
It's not only the train, but also the information. No. Well, I'm guessing that the question is about how to if I have a need to get this data to my phone from the wagon, going through the platform. This is yeah. For as far as I understand, this is a matter. This is possible, and this is a matter of configuration. If the solution is capable of doing that, you instantiate, you register. You can say that you register to the information you want, and the system will distribute to you the information you want through the interface that is in place for your device. So if your device is a smartphone application that gets data from a database, we can afford for the system to push the data specifically tagged for you if you need the data for you, I mean for specific application and not on the world, and then you can just connect to your data, and you know that the provision of the data is done by the platform. Of course, you need some reliability in terms of working of the platform, because the day you don't get your data, that's the issue of managing the abstraction in solution today. You put abstraction is very convenient when it works, and if you have something that is not working, but the abstraction makes it more difficult to find what is not working. So you need to think also when building abstraction in such application, you need to anticipate some problems that you can get and try to implement the means that allows you to resolve future problems. For us, for example, we keep also the platform is managing the application data, but in parallel, it manages also the control plan. We say the control plan is the data necessary for the system to work, but it's not for the user, it's for the administrator of the system. This data also needs to support the same mechanisms, because the system evolves, so the control plan of the system evolves, and we need to be able to diagnose what is not working if we get problems. So we are really interested to discuss if you have, even at high level, if you have some challenges or some use cases that pose some challenge in terms of collection of data from with maybe not all the challenges, but if you have a challenge in terms of managing some heterogeneity, or managing evolution of the system, anticipating some evolution, or managing maybe proprietary protocols in your solution in a way that is convenient for your business, we can help you.